And to begin with,
let's create a cosmic catastrophe. Imagine that all of a sudden, and without any warning, the sun vaporizes and completely disappears.
now let's replay that catastrophe and see what effect it would have on the planets according to Newton. Newton's theory predicts that with the destruction of the sun, the planets would immediately fly out of their orbits, careening off into space.
In other words, Newton thought that gravity was a force that acts instantaneously across any distance, and so we would immediately feel the effect of the sun's destruction.
Einstein came to think of the three dimensions of space and the single dimension of time as bound together in a single fabric of space-time. It was his hope that by understanding the geometry of this four-dimensional fabric of space-time, that he could simply talk about things moving along surfaces in this space-time fabric.
Like the surface of a trampoline, this unified fabric is warped and stretched by heavy objects like planets and stars. And it's this warping or curving of space-time that creates what we feel as gravity.
A planet like the Earth is kept in orbit not because the sun reaches out and instantaneously grabs hold of it, as in Newton's theory, but simply because it follows curves in the spatial fabric caused by the sun's presence. So, with this new understanding of gravity, let's rerun the cosmic catastrophe. Let's see what happens now
If the sun disappears. The gravitational disturbance that results will form a wave that travels across the spatial fabric in much the same way that a pebble dropped into a pond makes ripples that travel across the surface of the water. So we wouldn't feel a change in our orbit around the sun until this wave reached the Earth. What's more, Einstein calculated that these ripples of gravity travel at exactly the speed of light.
And so, with this new approach, Einstein resolved the conflict with Newton over how fast gravity travels. And more than that, Einstein gave the world a new picture for what the force of gravity actually is. Its warps and curves in the fabric of space and time.
Einstein called this new picture of gravity general relativity.
The unification of his new picture of gravity with the only other force known at the time, electromagnetism.
Now, electromagnetism is a force that had itself been unified only a few decades earlier. In the mid-1800s, electricity and magnetism were sparking scientists' interest. These two forces seem to share a curious relationship that inventors like Samuel Morse were taking advantage of in newfangled devices such as the telegraph. The relationship between electricity and magnetism was so obvious in nature that it demanded unification. If you've ever been on top of a mountain during a thunderstorm, you'll get the idea of how electricity and magnetism are closely related.
When a stream of electrically charged particles flows, like in a bolt of lightning, it creates a magnetic field, and you can see evidence of this
On a compass. Obsessed with this relationship, the Scot was determined to explain the connection between electricity and magnetism in the language of mathematics. Casting new light on the subject, Maxwell devised a set of 4 elegant mathematical equations that unified electricity and magnetism in a single force called electromagnetism. Scientists found that gravity and electromagnetism are not the only forces ruling the universe. Probing the structure of the atom, they discovered two more forces. One, dubbed the strong nuclear force, acts like a superglue, holding the nucleus of every atom together, binding protons to neutrons. And the other, called the weak nuclear force, allows neutrons to turn into protons, giving off radiation in the process. At the quantum level, the force we're most familiar with, gravity, was completely overshadowed by electromagnetism and these two new forces. Schwarzschild figured out that an enormous amount of mass, like that of a very dense star, concentrated in a small area, would warp the fabric of space-time so severely that nothing, not even light, could escape its gravitational pull. For decades, physicists were skeptical that Schwarzschild's calculations were anything more than theory. But today, satellite telescopes probing deep into space are discovering regions with enormous gravitational pull that most scientists believe are black holes. Schwarzschild's theory now seems to be reality.